All right, I hope you had the chance to explore with that applet. And of course, if these functions weren't enough for you to play around with, you can create your own by changing the values in that applet as much as you like, to your heart's content. So this first one, x was going to infinity. That means we're going way, way off to the right. So we don't care what happens over here to the graph. We just care what happens to the y values as x gets very, very big. And as x gets very, very big, the y values keep getting closer and closer and closer and closer to what number? I hope you all agreed with me that the answer was 0. The y values might never get to 0. In fact, in this case, they don't ever get to 0. But that is the one single number that they keep getting closer and closer and closer and closer to. So like if your friend thought the answer was 0.1 and you thought the answer was 0, you would be able to win the argument with your friend because the graph eventually crosses underneath 0.1 and then starts to move away from your friend's y value of 0.1 and closer to your y value of 0. Just to be clear, we're looking at these limits in a very intuitive and informal way. We've got stuff on the website in the graduate seminar portion of this with all the careful details about limits, and you're all welcome to check those out if you really want to see the real formal, careful definition of these limits. But all that we need is to understand intuitively and informally how these work. This function we've got at the same graph. I hope you recognize that the heart of this is the graph of 1 over x squared, and then we've done some shifts and stretches to it like we learned last week. So we started with our 1 over x squared. We multiplied by 2, which did a vertical stretch. So imagine taking this graph here, stretching it vertically. It looks pretty much the same. But then we do this plus 3, and that takes the graph and it shifts it up 3 units. So now this horizontal asymptote that used to be down here at y equals 0, the plus 3, as we learned last week, shifts the graph up 3 units. Now we've got a horizontal asymptote at 3, meaning that now when x goes off towards infinity, the y values here get closer and closer and closer to 3, not to 0. And I'm looking at these graphically because that was how the applet was and because this is one nice way to try to answer these problems. But you can also answer them purely by thinking about numbers. If you think about plugging in a huge, huge number for x, when you square a huge number, you get an even more huge number. When you take 2 divided by a very, very huge number, you get a number very, very close to 0. And when you add a number very, very close to 0 to 3, you get a number very, very close to 3. So another way to do this is without looking at the graphs, just thinking about numbers. All right, here we had our graph of 1 over x cubed, which looked very similar to 1 over x, as we discussed. We multiplied this time by 3, which stretched it vertically by a factor of 3, but also a negative, which flips us around the x-axis. So this part of the graph, which used to be up here, got flipped underneath, and we shifted up 4 units. So now, as x is going to negative infinity, we're going way, way off to the left now. That's what the negative infinity means. What are these y values getting closer and closer to? And they are getting closer and closer to 4. And it doesn't matter whether they're getting closer and closer to 4 from above or below. So for example, if this question had said, as I thought it did say about 10 seconds ago, that x was going to positive infinity, the answer would still be 4 because we're getting closer and closer to y values of 4 from underneath. But it doesn't matter whether we're coming from underneath or above. In either case, we're getting closer to 4 from this side or from that side. So if this had said positive infinity, the answer still would have been 4. All right, how about this one? X is getting close to 0. Now, that doesn't mean x equals 0. If somebody asks you, what is the value of this function at 0? The answer is undefined. We're not allowed to divide by 0. This means what happens when x gets very, 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 very near 0. So imagine you're plugging in a very, very tiny number, something like right in here or right in here, and you're looking to see what is happening to your y values. And you can see that as x gets closer and closer to 0, whether we're coming from the right side or the left side, the y values just keep going up and up and up without any bound. And so we write that this limit equals infinity, positive infinity, because these y values will eventually get up to 1,000, and then 10,000, 100,000, a million, a billion, a trillion, a quadrillion. They will get up and they will exceed any number that you can think of. And that's what we mean when we say that the limit equals infinity. Now this one is really interesting. X is approaching 0, 1 over x. If I'm coming from the right side, it seems like the answer should be positive infinity. If we're coming from the left side, the answer should be negative infinity. But when I just write x is approaching 0, we don't know which side we're approaching from. And limits are like functions. There's got to be only one unique answer. So if there's ever any doubt and a limit is approaching a different thing from one side than from the other side, then we say that the limit does not exist. We do not say the limit is infinity and negative infinity. You cannot have multiple answers for a limit, just like you cannot have multiple outputs for a single input in a function. But we still would like to be able to indicate what is happening as x approaches from one side, and that's where we use this nice notation that we discussed before at the end of the last segment. This says x is approaching 0 from the right side, meaning we know we're not worrying about this part of the graph. We're only plugging in x values here, 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 here. And when x gets very close to 0 but positive, the y's get very, very big and positive. So the answer here is positive infinity. If you want to think about this again without thinking about the graph, what kind of x value are you plugging in? You're plugging in a very, very tiny positive. So if you take 1 over positive 0.00000001, you will get a very, very big and positive answer. So that's why this is going to positive infinity. And then on this side, we're approaching 0 from the left. So now we're coming down this part of the graph. We don't care about this part at all. And as x gets close to 0 from the negative side, from the left, the y values head down towards negative infinity. They just keep going down and down and down. They get below any negative number you can think of. They'll get to negative 1,000, negative 1,000,000, negative 1,000,000,000. They'll go below any number that you can imagine, any negative number that you can imagine. So our main thing with this was to get some more exposure to limits, because we're going to be doing a lot of limits next week when we start calculus. And one thing that I discovered early in my teaching is that if we haven't done limits before this, students start to think that this thing in calculus that we're going to learn that's called the derivative is the same as a limit. But what I want you to remember is that we have already done one limit last week and 8 limits here today, 7 limits here today, and we haven't even talked about anything about calculus officially. So we can do limits that have nothing at all to do with calculus. And now we have a check your understanding quiz for you to see how well you have understood all of this stuff.